Doppler Shift.
The Doppler Shift is a physics phenomenon that applies to both light and sound. As we know, both light and sound travel in waves. So in order to understand the Doppler effect, we need to understand waves. So we're going to review that really quick. I drew up here an example of a wave. Wavelength is the distance from one crest of a wave to the next crest. And the frequency is the number of waves that are going to move through a certain point in 1 second. Sound waves have wavelengths and frequencies, and light waves have wavelengths and frequencies. For sound, the way that we perceive frequency is through pitch. So if we've got a note, if we got a piano, we play a higher note, we're going to have a higher frequency, it's going to be a higher pitch. The wave is going to look more like this as opposed to this. And if we play a lower note, then our frequency is lower, our wavelength is longer, and it's a lower pitch. The way that we perceive differences in frequency of light is through color. And I drew up here Roy G. Biv. That's violet, indigo, blue, green, yellow, orange, red. Higher frequencies correspond to colors closer to violet. So the reason that you're seeing blue is because it has a higher frequency than green, for example. In case you're wondering, that car video in here was not a mistake, that was on purpose. That is a perfect example of the Doppler shift with sound. And so I'm going to break that down for you guys, what happened, why does the pitch shift when the car moves past the camera, why does the pitch change from a higher pitch to a lower pitch, from a higher frequency to a lower frequency. Now, so if we just have our car here and it's sitting there, it's stuck in traffic, just honking its horn, the waves coming out are going to look like that. They're going to go out evenly in all directions. This is another way to draw a wave model. Just picture these waves as the crests of this wave. Now, we're going to say, in this example, our car was moving towards the observer for half of the video and then away from the observer for the rest of the video. And so when it's moving in that direction, it's letting out waves, and when the car's moving, it'll let out a wave of sound, and then it's moving towards the observer, so it's going to be closer to the crest of the wave that it let out in the direction of the observer than it is to the crest of the wave that it let out behind it. And so the waves are going to start looking to the observer. The waves appear to be something more like this. And so as you notice here, there are more crests packed together, and so it's a higher frequency. So when this group of waves reaches our observer, it appears that the wave has a higher frequency, it's a higher pitch. And then we're going to say our car keeps moving, it passes, and then it's still letting out the waves here, but like I said before, now it's moving away from the observer, and the waves are still looking the same. So to the observer, the crests of our wave are farther apart, our wavelength is longer, our frequency is less, and so the waves look different, and they are picked up on a lower frequency. That's why at this point right here, it moves from a high frequency to a low frequency. So like I said before, the Doppler shift also applies to light. But that's only when the source of the light is moving at a velocity that's close to the speed of light. And for an example, we're going to talk about galaxies. And we're going to assume that these stars are two different galaxies. This is our observer here. This is Earth. And we're going to be talking about a galaxy that's moving away from Earth at close to the speed of light. And it's going to be doing the same thing that the car would be doing. The waves at the light source are one way, but to the observer here, because it's moving away, the frequency of the wave is going to appear lower than it actually is, and so it's going to be closer to red. The light is going to appear more red than in reality it is as it comes out of the source. And so that's what we call redshift. If the galaxy is moving towards the Earth, then we can compare it to when the car was moving towards our observer, and there are more crests in the same amount of space, and so it's a higher frequency, and violet light has a higher frequency than red light, and so it's going to appear more blue. The light is going to appear more blue than it actually is coming out of that galaxy, and so we call that a blue shift. So this is an example of the Doppler shift with light. Now that we've got those examples in your head of how the Doppler shift affects sound and how it affects light, we're going to break down the math behind what's going on. So this is the equation for the Doppler shift of a sound wave, and this is the frequency of the wave as observed by our stationary observer. This is the frequency of the sound at the source. This is the velocity of sound. Both of these V's are the velocity of sound. This is the velocity of our observer. And in this case, it was stationary, so it was 0. This is the velocity of our source. So that's the car's velocity towards the observer. So in this example, let's calculate the frequency that our person was hearing. So the frequency of the source, we're just going to say that's 300 hertz. The velocity of sound is 343, and that's -0 in this case. And this because the source is moving towards our observer, we're going to use minus because we want our denominator to be smaller. And we would use plus. It doesn't matter because it's 0, but we want our numerator to be greater because we're moving towards, so we're going to have a higher frequency. So the final answer on this is going to be 301.01 hertz. That's the frequency that our observer is hearing. And notice 301.01 hertz is greater than 300 hertz. That's a higher frequency, higher pitch when you're moving towards our observer. Now when we're moving away from our observer, it's still 300 hertz. It's still 343 over 343, and this time we're going to add 5 because now we're talking about when the car has passed our observer and is moving away. And that's going to give us a final answer of 295.67 hertz. And that is lower than our frequency at the source, and therefore it's a lower pitch. So now that we've talked about how the Doppler shift affects the numbers in sound, we're going to talk about how the Doppler shift affects the numbers in light frequencies. So while I'm going through this, remember the example that I had up here of the two stars. So the frequency as observed on Earth, this is the frequency of the galaxy, the frequency of the light that the galaxy is giving off. U is the velocity of the galaxy itself relative to Earth. A positive value for U is going to be a value that's moving away, and a negative value for U is going to be when the galaxy is moving towards Earth. C is just the speed of light. So frequency of light that hits the Earth, we're going to say 10 to the 6th hertz there for the frequency of the light that's leaving the galaxy. And we're going to say that it's 0.825 multiplied by the speed of light. That's the velocity of our galaxy. You'll notice that 0.825 times the speed of light, that is very close to the speed of light itself. So that's why we have to switch equations. It's because our source is moving extremely fast. And 1 plus 0.825c divided by c there. If you'll notice, our c's cancel out. And this is when we're talking about the galaxy moving away, because our U value here is positive. It fits right into this equation perfectly. And so we come up with the frequency of the light that hits the Earth is 3.09 times 10 to the 5th hertz. Now, 3.09 times 10 to the 5th, that is a smaller value than the 10 to the 6th hertz coming out at the source. So that's why this is a red shift. That's what we call red shift. It's lower frequency, closer to red. Red has a low frequency. So now when we're moving towards, the frequency that hits Earth is, so the source frequency is the same. We're going to do square root 1. Now we're going to say this is a negative value here, negative 0.825c. And then this is plus a negative 0.825c divided by c. Do all the math on that, we come out with 3.23 times 10 to the 6th hertz. Now you'll notice 3.23 times 10 to the 6th hertz is greater than just 10 to the 6th hertz. And so just like when the star was moving towards us, when the car was moving towards us, the frequency is greater because the waves become more bunched. They appear more bunched to us. And that is an example of blue shift. The light is going to look more blue to the observer on